Okay, question 2.1. We have some number patterns here, and this is a geometric number sequence that is made up of an arrangement of matchsticks. So first of all, I just want to point out that with these diagrams, we immediately want to convert these diagrams back into numbers. We don't want to work with pictures really. So first of all, this is still term 1. The second picture is still term 2, and that is term 3. And we are simply going to properly count. Please be careful if you see this in your worksheets, exercises, control tests, whatever. Make sure that you are counting the stuff properly, because the stuff can be anything. It can be matchsticks or marbles or I don't know, whatever. So please make sure that you count the number of stuff in each diagram properly. So the first set of matchsticks, I'm counting here 9. So let's just write there 9. And then for the second one, they've added another 4. So 9 plus 4 is 13. And then for the third one, we've got so that's 13 plus another 3 is 16 plus 1 is 17. Okay, of course, again, please, even if you must go count them individually and make sure, then do that. So we've got 9, 13, and 17. So if I transfer that to our sheet over here, so 2.1.1, we have a pattern or sequence that starts with 9, goes on to 13, and goes on to 17, and may continue. And the first question is to determine the constant difference of the above sequence. So the above sequence, of course, is that. And the difference, if I go from 9 to 13, I have a, 4? That's plus 4. And then from 13 to 17 is again plus 4. So it appears that our constant difference here is plus 4. So 2.1.1 D is equal to plus 4 or just 4. Right. Then 2.1.2, determine the general rule for the sequence, or determine the nth term. Give us the nth term. Right. So we said that we are trying to, or we usually try to couple or link the constant difference to the term position, and we can use the first term. So we can use term 1. We use term 1 because it's easier to multiply with 1, because it makes the calculation simpler. So term 1 is equal to 9. And if I take my constant difference of 4 and I multiply it with 1, which is the term position, in this case here I'm going to say, okay, that's 1 and that's 1, so that's the one I'm talking about. So 4 times 1 is 4, which is of course not equal to 9. So what must happen to the product of 4 times 1, which is 4, to make it equal to 9? So 4 plus 5 will give me 9. Now I'm just going to test this, just to again just prove that it is the rule that will work. What happens if I do it with term 2? So term 2 is equal to 13. If I take my constant difference and multiply it with 2, which is the position here, the second term, in other words, that's the 2 I'm talking about, and if I add 5, so 4 times 2 is 8, 8 plus 5 is 13, so it works. And then lastly, let's just do it for term 3 as well. So term 3 is equal to 17 in this case, and that's again, if I take my constant difference of 4, multiplied by the position, which is 3, in other words, that 3, and if I add 5, what happens? 4 times 3 is 12, 12 plus 5 is 17. So it seems that the rule then is, if I take my constant difference of 4 and I multiply it with any position, with my term position, and I then add a 5, I will get the value of the term in that position. So in other words, my general rule is 4n plus 5. 2.1.3, again now use our rule, or use your rule to calculate the 25th term. So that means I will take the rule that I've calculated here, and I'm going to calculate the 25th term in this case. So T25 is equal to 4 times 25. So in other words, wherever I see the n, I will replace now with a 25, and I'll add a 5. So 4 times 25 is 100, plus 5 is 105. So 4 times 25 is 100, plus the 5 gives us 105. And that is my 25th term done.